Welcome to Mysteries of the Universe. I'm your host, Ben Carter, and in today's episode we confront a mind-bending possibility that challenges everything we think we know about existence, the multiverse theory. What if our universe is just one of countless others, each with its own laws of physics, dimensions of time, and versions of reality? Could the cosmos be far stranger and far bigger than we've ever imagined? The story of the multiverse doesn't begin with science fiction, but with mathematics. In the early 20th century, as physicists sought to understand the nature of the cosmos, they developed powerful new frameworks to describe the universe. Frameworks that eventually led to the notion that what we call the universe might be only a fragment of a much larger, possibly infinite reality. The seeds were sown with Einstein's theory of general relativity, published in 1915. For the first time, space and time were not static backgrounds but dynamic entities, flexible, warping in response to mass and energy. The fabric of the universe, it turned out, could curve, stretch, and expand. Einstein's equations didn't predict a static cosmos. Quite the opposite, they implied a universe that was either expanding or contracting. But at the time, the idea of an expanding universe was philosophically uncomfortable. Einstein famously introduced a term he called the cosmological constant to keep his equations balanced, to avoid what they seemed to insist, that the universe had a beginning and was growing. It wasn't until 1929, when Edwin Hubble observed that galaxies were moving away from us in every direction, that the reality of an expanding universe became unavoidable. As the science progressed, so did the puzzles. In the 1960s, the discovery of the cosmic microwave background radiation, the afterglow of the Big Bang, cemented the idea that the universe had a hot, dense origin point. But this created new questions. What came before? Why is the universe so uniform in all directions? Why does it appear so flat, geometrically speaking? To answer these questions, physicists developed the theory of cosmic inflation. In the 1980s, Alan Guth proposed that in the earliest fractions of a second after the Big Bang, the universe underwent a period of exponential expansion, faster than the speed of light. This inflation smoothed out the wrinkles in the fabric of space-time, explaining the universe's large-scale uniformity. But inflation had a strange side effect. Under certain models, it didn't stop everywhere at once. Instead, inflation might continue indefinitely in some regions, creating bubble-like pockets of space that stop inflating and evolve into universes of their own. This concept, eternal inflation, laid the groundwork for a modern multiverse model. Meanwhile, quantum mechanics, the theory governing the behavior of particles at the smallest scales, added its own bizarre twist. In 1957, physicist Hugh Everett proposed what became known as the many worlds interpretation of quantum mechanics. Rather than collapsing into one outcome when observed, quantum systems might branch into all possible outcomes simultaneously. Each possibility, according to Everett, creates a new, separate universe. In one world, a particle goes left. In another, it goes right. In one reality, you made a phone call. In another, you didn't. The multiverse, in this view, becomes a branching tree, infinitely splitting with every quantum decision. These theories, cosmic inflation and quantum many worlds, arose from different scientific motivations, but both point toward a startling conclusion, that what we call the universe may not be the whole of existence, but just a sliver of a much grander structure. The laws of physics that govern our reality might be local, not universal. Other regions could operate under entirely different rules, different particles, different dimensions, even different concepts of time. Ancient ideas hint at similar possibilities. Hindu cosmology speaks of an infinite cycle of universes being created and destroyed. Buddhist teachings describe countless world systems, each with its own histories and laws. In some interpretations of Kabbalistic mysticism, layers of reality unfold in infinite gradations, each mirroring or influencing the others. These visions, though mythological or symbolic, resonate with the modern idea that our universe is not alone. As the 20th century gave way to the 21st, string theory emerged as a leading candidate for a theory of everything, a unifying framework to reconcile gravity and quantum mechanics. But string theory came with an unexpected feature, a nearly infinite number of possible solutions. Each solution describes a different universe with its own physical constants and properties. This so-called string landscape added a new layer of credibility to the multiverse. If the mathematics allows for countless versions of reality, perhaps they all exist somewhere. The question then shifted. No longer was it simply, is there more than one universe, but how many kinds of multiverses are there, and what are the mechanisms that generate them? As theories multiplied, so did the interpretations. Some were grounded in physics, others in philosophy, but all pointed toward a disorienting, humbling realization. The universe we know may be just one frame in a film strip that stretches forever. Evidence for the multiverse, at least in its more grounded scientific forms, is subtle, embedded in the edges of observation, the oddities of data, and the unexplained coincidences of the cosmos. It does not arrive with the certainty of direct detection, but with patterns and anomalies that resist easy explanation. Among the most often cited is the remarkable fine-tuning of the physical constants that govern our universe. The values of these constants, the strength of gravity, the charge of the electron, the cosmological constant, are so precisely calibrated that even a slight variation in any one of them would render the formation of stars, planets, or life impossible. This extreme specificity has led some physicists to suspect that our universe may not be uniquely tailored, but simply one of many, each with different settings. In a vast multiverse, most universes would be sterile or chaotic. But a few, by chance alone, would have the right parameters to allow complexity to arise. We happen to live in one of those rare universes, not because it was designed for us, but because only in such a universe could we exist to ask the question. This line of reasoning is known as the anthropic principle, and while it remains controversial, it has become a key element in multiverse discussions. The cosmic microwave background, the faint radiation left over from the Big Bang, offers another intriguing clue. It is the most ancient light in the universe, and its delicate fluctuations offer a snapshot of conditions just 380,000 years after the Big Bang. Instruments like the Planck satellite and the Wilkinson microwave anisotropy probe have mapped this radiation with extraordinary precision. In the patterns of this ancient light, scientists have noticed subtle anomalies, unexplained cold spots and asymmetries that don't neatly fit within standard cosmological models. One such anomaly is the so-called cold spot, a region of the sky significantly cooler than the surrounding areas. While it may be a statistical fluke, some theorists have suggested more exotic explanations, including the idea that it could be a bruise, an imprint left from a collision between our universe and another bubble universe during the early moments of cosmic inflation. If true, it would be the first indirect observational hint of another universe brushing against our own. But these suggestions remain speculative. The signals are faint, the data complex, and alternative explanations exist. The cold spot, for instance, might also be caused by a massive void in space, a region with less matter, which could produce the observed cooling effect. Still, the possibility of a multiversal collision has not been ruled out entirely, and researchers continue to analyze the microwave background for further anomalies. In the realm of quantum physics, evidence is even more elusive. The many-worlds interpretation does not predict new particles or cosmic signatures. Instead, it offers an alternate framework for understanding existing phenomena. It challenges the traditional idea of wave function collapse, that a quantum system reduces to one outcome when measured, and replaces it with a branching structure in which all outcomes happen, each in its own universe. Since these branches do not interact, they remain invisible to us. The theory makes no observable predictions that differ from standard quantum mechanics, which makes it difficult, if not impossible, to test directly. Still, there are physicists and philosophers who argue that the coherence and simplicity of many worlds make it compelling. It eliminates the need for randomness and mysterious collapses, replacing them with a single deterministic multiverse in which every possible history unfolds. Some have proposed that advances in quantum computing might eventually allow us to probe the structure of these branches indirectly, though such ideas remain in the theoretical realm for now. In string theory, the evidence is mathematical. The landscape of possible universes, each with its own laws and constants, is not observed but derived from the flexibility of the equations themselves. The theory allows for 10 to her 500 different solutions, each corresponding to a different universe in the multiverse. Again, this vast possibility space is not proof, but it demonstrates that physics does not inherently limit us to just one kind of universe. Taken together, the data does not confirm the existence of the multiverse, but it paints a portrait of a cosmos that may be far more complex than previously imagined. The boundaries of observation stretch only so far. Beyond them lies a realm where logic and math suggest a multitude of realities, but where the tools of science strain to reach. For now, the multiverse remains an elegant solution to a number of profound puzzles, one that aligns with the known data, while opening doors to realms we cannot yet see. The landscape of mainstream scientific thought on the multiverse is a layered terrain, shaped by competing theories, rigorous mathematics, and interpretations of cosmological data. While the concept of multiple universes may seem speculative, even fantastical, many respected physicists treat it as a serious consequence of well-established theories. Rather than being a fringe idea, the multiverse emerges naturally from frameworks already used to explain the structure of space-time, the behavior of particles, and the evolution of the early universe. In the inflationary model of cosmology, one of the dominant paradigms in modern astrophysics, the multiverse arises almost inevitably. Alan Guthr's original idea of cosmic inflation was expanded by André Linde, who introduced the concept of chaotic inflation, a version of the theory where inflation doesn't stop everywhere at once. Instead, some regions of space stop inflating and form bubble universes, while other areas continue to expand. This leads to a kind of cosmic foam, with bubbles branching out endlessly, each becoming its own universe with potentially distinct physical laws. Linde has argued that this structure, eternal inflation, implies a self-replicating or infinite multiverse, where universes bud off from one another like cells dividing in an unending process. This branching picture is not considered a wild extrapolation by its proponents, but a direct consequence of the equations governing inflation. If the inflationary field has certain properties, specifically, if it has a flat enough potential energy curve, then the quantum fluctuations that occur during inflation ensure that new bubble universes are constantly being spawned. Our universe, then, is simply one pocket where inflation ended and the familiar laws of physics emerged. Parallel to this cosmological version of the multiverse is the quantum mechanical interpretation introduced by Hugh Everett. The many worlds interpretation is not an add-on to quantum theory, but an alternate reading of it. It takes the math of quantum mechanics at face value and assumes that all outcomes of quantum measurements actually occur, each in its own non-communicating universe. This framework avoids the troubling problem of wave function collapse and the observer's role in determining reality. Instead, reality is a branching tree of ever-dividing possibilities, with each decision or measurement spawning countless new universes. While many worlds remains controversial, it is supported by some of the most respected names in physics. Nobel laureate Steven Weinberg, physicist David Deutsch, and cosmologist Max Tegmark have all publicly expressed their support for its conceptual clarity. Deutsch, in particular, has argued that quantum computing provides indirect support for the idea, as quantum algorithms seem to rely on parallel computations occurring in multiple branches of the wave function. Then there is string theory, which provides its own foundation for a multiverse, though of a different flavor. String theory attempts to reconcile gravity with quantum mechanics by proposing that all fundamental particles are not point-like dots, but tiny vibrating strings. These strings can exist only in a universe with extra dimensions, typically 10 or 11 total. But string theory doesn't predict a unique universe. Instead, it allows for a multitude of possible configurations known as vacua, each with different shapes for these extra dimensions and different values for the physical constants. This vast array of possibilities is called the string landscape. Each configuration describes a different possible universe. When combined with the process of inflation, these various vacua could be physically realized in different bubble universes. Leonard Susskind, one of the founders of string theory, has argued that this multiverse view is not just a consequence of the theory, it's necessary for it to make sense. The string landscape explains why our universe appears fine-tuned. We live in one of the many possible universes where the conditions happen to allow life. Even within the field of cosmology, the idea of a multiverse is used to address persistent puzzles. The small but non-zero value of the cosmological constant, responsible for the acceleration of the universe's expansion, has long baffled physicists. The multiverse provides a natural solution. In most universes, the constant is too large or too small for galaxies to form. In ours, it happens to be just right, not because of some deep principle, but because observers like us can only emerge in a universe where that constant permits complexity. Taken as a whole, these mainstream models suggest that the multiverse is not a wild leap, but a natural extrapolation of existing physics. It arises not from fantasy, but from the equations that already describe our universe with remarkable precision. And while direct observation remains out of reach, the multiverse remains a scientifically viable and deeply unsettling possibility. Despite its theoretical foundations, the multiverse concept remains one of the most hotly debated ideas in modern science. For every physicist who sees it as a logical consequence of established models, there are others who question its scientific legitimacy. The core of the debate centers on one fundamental issue: testability. If we cannot observe, measure, or interact with other universes, can the multiverse ever be considered part of empirical science, or is it merely metaphysical speculation dressed in mathematical clothing? This divide has sparked intense discussion within the scientific community. Critics argue that a theory must, at its core, be falsifiable. This principle, articulated by philosopher Karl Popper, states that for a hypothesis to be scientific, it must be possible to prove it wrong. By this measure, the multiverse faces a serious challenge. If other universes are causally disconnected from our own, beyond our light cone, inaccessible to any form of observation, then how can we ever test the theory? Some physicists counter that untestable predictions are not unique to the multiverse. Certain aspects of string theory, for instance, remain far beyond current experimental capabilities, yet the theory continues to drive research because of its internal consistency and explanatory power. In this view, the multiverse is not a standalone theory, but a consequence of theories we do consider scientific. If eternal inflation, quantum mechanics, or string theory are supported by evidence, and those theories imply a multiverse, then it is reasonable to consider the multiverse a scientific possibility, even if it cannot yet be directly tested. But others are not so forgiving. Physicist Paul Steinhardt, one of the original architects of inflation theory, has become a vocal critic of the multiverse idea. He argues that inflation has become so flexible in its predictions that it explains everything and nothing at once, making it impossible to rule out. In such a landscape, he warns, theoretical physics risks drifting away from empirical grounding and toward a model of science that values elegance over evidence. This concern is echoed by others who fear that the multiverse allows for too much. If every possible outcome happens in some universe, then what meaning can be attached to prediction or probability? How can science explain anything if it ultimately explains everything? These questions point to a philosophical tension beneath the surface, between the desire for a coherent framework that unifies all observations and the need for theories to make specific, testable claims about reality. There are also challenges within the theories that generate multiverses. In the many worlds interpretation, the branching of universes is mathematically elegant, but conceptually difficult. If new universes are constantly being created with every quantum event, where is the mechanism that allows this branching to occur? What does it mean for these branches to be real if they can never be detected? Proponents argue that the mathematics supports it, but critics point out that without observational consequence, the theory remains ontologically extravagant, multiplying realities beyond necessity. In eternal inflation models, the problem of measure becomes acute. If an infinite number of universes exist, how do we assign probabilities to events? How do we define typical outcomes in an infinite ensemble? This issue, known as the measure problem, has plagued multiverse cosmology for decades. Without a clear way to weigh the significance of different universes, making predictions becomes mathematically ambiguous and conceptually unstable. Even the anthropic principle, often invoked in defense of the multiverse, has its detractors. Some scientists view it as a tautology, an empty explanation that avoids deeper inquiry. Saying we live in this universe because it supports life explains nothing unless there is an underlying mechanism that determines the distribution of universes and the emergence of observers. Otherwise, the anthropic principle risks becoming a conversation stopper rather than a scientific tool. These criticisms do not render the multiverse impossible or invalid, but they highlight the fragile line it walks between science and philosophy. The idea challenges traditional scientific boundaries, forcing physicists to grapple with the limits of observation, the role of theory, and the nature of explanation itself. Whether the multiverse is a bold frontier or a dangerous distraction remains unresolved. What is clear is that the multiverse is not just a scientific idea, it is a conceptual revolution. It asks not only whether we are alone in the cosmos, but whether the cosmos is even the right word. If the multiverse is real, then our universe is not the whole of existence. It is one chapter in an endless library, a single page in an infinite book. And with that realization comes a profound shift in how we define reality, meaning, and our place in the grand design. Outside the bounds of established science, the multiverse has inspired a wide range of speculative and fringe interpretations. These ideas, while often lacking empirical support, reflect deep human curiosity and a willingness to explore the unknown. They span the realms of philosophy, metaphysics, and theoretical imagination, suggesting that the multiverse may be more than a scientific concept. It may also be a mirror, reflecting our hopes, fears, and the longing to understand what lies beyond the visible. One of the most well-known speculative takes is the parallel lives interpretation. In this view, every possible version of ourselves exists somewhere in the multiverse. There is a universe where we made a different choice in a pivotal moment, where history took a divergent path, where entire civilizations rose or fell based on a single altered event. This idea, while rooted loosely in the many worlds interpretation of quantum mechanics, goes further, imagining fully formed alternate realities in which our lives play out in infinite variations. It resonates deeply with cultural storytelling, from science fiction literature to films like Sliding Doors or Everything Everywhere All at Once, which portray these overlapping timelines with emotional and existential weight. Another fringe theory posits that some people may have experienced subtle slips between universes. Reports of Mandela effects, where large groups remember events or facts differently than how they appear in recorded history, are sometimes interpreted by believers as evidence that individuals have shifted between slightly different versions of reality. The term originates from the widespread but incorrect memory that Nelson Mandela died in prison during the 1980s, despite his actual release and presidency in the 1990s. While psychologists attribute this phenomenon to collective false memory, a small but vocal subculture claims it points to deeper, unexplained changes in the timeline, potential evidence of multiversal interference. In metaphysical and spiritual circles, the multiverse has been adopted into models of consciousness and soul evolution. Some esoteric teachings suggest that the soul incarnates not just in a linear sequence of lifetimes, but simultaneously across multiple realities, learning different lessons, facing alternate challenges, and expanding awareness across the multiversal spectrum. This framework borrows language from quantum theory and applies it to the inner life. Reincarnation becomes multidimensional rather than chronological. Karma and fate stretch across universes, and awakening to this layered existence is seen as a kind of spiritual enlightenment. There are even ideas, deeply speculative though they may be, that advanced civilizations within the multiverse might one day learn to navigate it, traveling not through space but across realities. Theoretical physicist Michio Kaku has spoken about the potential for Type 3 civilizations, those capable of harnessing the energy of an entire galaxy, to manipulate space-time on a multiversal scale. These civilizations, if they exist, might not be bound by a single universe at all, but instead exist across many, using dimensions we cannot perceive to traverse realities as easily as we cross continents. In some fringe cosmologies, the multiverse is seen not just as a physical structure, but as a system of nested simulations. This idea intersects with the simulation hypothesis, which posits that our universe may be an artificial construct created by an advanced intelligence. If such simulations are possible, then simulated universes could exist within simulated universes, a recursive stack of realities, each with its own rules and parameters. In this view, the multiverse is both a computational phenomenon and a spiritual metaphor, a layered architecture in which each level of reality is as real to its inhabitants as any other. These speculative interpretations often blur the line between science and narrative, between theory and myth. They reflect the human tendency to seek meaning in the unknown, to build frameworks that help us cope with the vastness and strangeness of existence. While they may not meet the standards of empirical validation, they play a vital role in shaping how the multiverse is imagined, discussed, and understood outside of academic circles. And in a way, they echo the same question at the heart of the scientific multiverse. What else is out there? What realities lie just beyond the reach of our instruments, our senses, our comprehension? Whether through physics or philosophy, theory or myth, the multiverse remains a vessel into which we pour our deepest speculations, not just about the universe, but about ourselves. The implications of a multiverse reach far beyond physics and cosmology. They strike at the core of philosophical inquiry, touching on identity, purpose, and the very structure of meaning. If our universe is one among many, perhaps an infinite number, then questions about our uniqueness, our choices, and our significance are fundamentally transformed. The multiverse challenges long-held assumptions about who we are and what it means to exist. One of the most profound philosophical questions raised by the multiverse is the nature of self. In a reality where every possible version of you exists somewhere, what does it mean to be you? Is identity a fixed essence, or is it a branching collection of outcomes, endlessly multiplying with each decision? If another version of you lived a life of heroism, or betrayal, or tragedy, does that reflect on you in any meaningful way? The multiverse invites a radical re-evaluation of personal responsibility and moral consequence. It suggests that the self is not a singular narrative, but a constellation of narratives, all unfolding in parallel. This leads naturally to questions of free will. If every possible decision is realized in some universe, then do choices matter? Are we truly deciding between options, or are we simply becoming one version of ourselves while other versions make the alternate choice? Some philosophers argue that the multiverse affirms free will by allowing all outcomes to manifest. Others suggest it undermines agency altogether, reducing personal action to a kind of narrative inevitability, every path walked by someone, somewhere, regardless of intention. There are also theological and spiritual implications. In many religious traditions, the universe is viewed as a deliberate creation, with humanity occupying a central role. The multiverse dilutes this notion by introducing an incomprehensible scale of existence. If countless universes exist, many with life, perhaps even with beings far more advanced than ourselves, what becomes of the idea of human specialness? Are we still the focal point of a divine plan, or a single thread in an infinite tapestry? Some theologians have attempted to reconcile the multiverse with belief by expanding the notion of divinity. If God exists, they argue, then a multiverse might be the most fitting expression of infinite creative power. Just as an artist paints not one canvas but many, a creator might generate not one cosmos but a vast spectrum of them, each embodying different aspects of possibility, beauty, and law. In this view, the multiverse becomes not a threat to spirituality, but an enhancement of it, a stage upon which infinite forms of life and consciousness are given room to exist and evolve. Others, however, find the concept troubling. If suffering exists in some universes but not others, does that make it arbitrary? If every horror and every joy unfolds somewhere, is the value of either diminished? These are not questions that science can answer, but they are questions that matter deeply to the human experience. They frame the multiverse not just as a physical structure, but as an ethical and emotional dilemma. Then there is the question of purpose. In a single universe, meaning might be found in the rare and precious nature of life. But in a multiverse where every possible life exists, does meaning persist, or does it dissolve into redundancy? Some argue that meaning becomes more profound in such a context, that it is not the rarity of a life that gives it value, but the experience itself. Even if a billion versions of you exist, only one is conscious to you, only one carries your memories, your sensations, your love and loss. In that sense, meaning is local. It does not need to be universal to be real. Still, the multiverse can provoke a deep sense of existential vertigo. It can make our lives feel small, even irrelevant, in the face of such immensity. But this reaction is not new. It echoes the way humanity once felt upon learning that Earth was not the center of the cosmos, or that the stars were not fixed points of light, but distant suns in an ocean of galaxies. Each revelation expands our perspective and challenges us to find new ways to understand our place within it. The multiverse, if real, is not a negation of human experience. It is a reframing. It tells us that reality is broader, stranger, and more intricate than we imagined. That our story is not the only one, but still uniquely ours. And in that recognition, perhaps, there is room for awe rather than despair, for curiosity rather than fear, for meaning not in spite of the multiverse, but because of it. As the contours of the multiverse take shape, through theories, debates, and the implications they carry, a coherent web of clues, patterns, and ideas begins to emerge. Each thread, while individually incomplete, contributes to a larger framework that hints at a reality far more expansive than previously imagined. From quantum mechanics to cosmology, from mathematical elegance to metaphysical reflection, the clues do not point in a single direction, but rather sketch the outline of a structure too vast and multidimensional to be captured from any one angle. One of the most compelling observations lies in the apparent fine-tuning of the universe. The precision of physical constants, the gravitational constant, the charge of the electron, the strength of the nuclear force, is not just convenient for life. It appears eerily precise. A slight alteration in any of these values would prevent the formation of stars, planets, or atoms as we know them. While some interpret this as evidence of design, the multiverse provides an alternative explanation. With an infinite variety of universes, each with different constants, it's statistically inevitable that some would support life. We simply happen to be in one where conditions allow for our existence. This anthropic logic, while unsatisfying to some, offers a rational framework that aligns with both data and theory. The cosmic microwave background, a thermal echo from the early universe, reveals another subtle clue. Its tiny temperature variations reflect the primordial fluctuations that seeded galaxies and structure in the cosmos. Most of the data matches predictions from inflationary cosmology with stunning accuracy, yet anomalies persist. The cold spot, an unusually large and cold region, defies simple explanation. Some propose it's just a random statistical fluke. Others suggest it might be evidence of a bruise, a mark left by a neighbouring universe that once collided with ours during its formative stages. Though highly speculative, the idea of cosmic collisions between universes is a natural extension of eternal inflation, where expanding bubbles of space-time could occasionally make contact. Quantum mechanics, while profoundly successful, remains interpretively unsettled. The many worlds interpretation provides a consistent, deterministic model that avoids the paradox of wave function collapse. It requires no hidden variables or special observers, just the acceptance that all outcomes happen, each in its own universe. Though invisible to us, these parallel branches are, in this framework, as real as the one we inhabit. The coherence of this model, despite its surreal implications, gives it a certain intellectual gravity. It doesn't force the math to bend around our preferences. It simply lets the equations speak. In the theoretical realm of string theory, the so-called landscape of solutions grows more important. With as many as 10,500 mathematically consistent universes, each one potentially realized in a separate bubble of the multiverse, the odds of finding ourselves in a life-permitting cosmos become less astonishing. The multitude becomes the explanation. Combined with inflation, these possibilities gain not just theoretical elegance, but a physical mechanism for realization. The mathematical structure of string theory doesn't demand a multiverse, but it allows for one, robustly and relentlessly. While none of these observations alone confirm the multiverse, together they form a pattern. A universe that seems too fine-tuned. Quantum rules that naturally multiply realities, cosmological models that breed universes like seeds on the wind. Mathematical frameworks that predict vast arrays of possibilities. The coherence of these ideas across unrelated fields lends them weight. They are not mere fantasies, they are the logical extensions of our most successful theories. But coherence is not confirmation. The boundary between what is plausible and what is real remains sharp. The multiverse may elegantly solve many mysteries, but until it yields observable consequences, it remains a hypothesis. Still, the clues suggest something. They whisper of a structure behind the veil. Not chaos, but possibility. Not randomness, but complexity layered upon complexity. If these clues mean anything, they point to a cosmos that is not singular, but plural. Not a lone universe, but a tapestry woven from every thread that could ever be. A multiverse. Not proven, but perhaps inevitable. Across this vast conceptual expanse, the multiverse stands not only as a scientific theory, but as a profound philosophical and intellectual turning point. It compels a reckoning with the way we define knowledge, truth, and the scope of human understanding. As we gather the fragments of theory, anomaly, and speculation, what emerges is less a finished picture and more a shifting mosaic, an evolving map of a reality that may be fundamentally beyond our comprehension, yet still deeply connected to our most intimate experiences of existence. Throughout the history of science, our understanding of the universe has been shaped by revolutions, each expanding the cosmic horizon. The Copernican shift displaced Earth from the center. The discovery of galaxies beyond the Milky Way extended the known universe from thousands of stars to trillions. The Big Bang introduced a beginning, and with it, the concept of cosmic evolution. Now, the multiverse presents the next potential upheaval, not of place or time, but of uniqueness. It suggests that the universe we inhabit may be only one note in a boundless cosmic symphony. This concept reframes every discovery. The laws of physics may not be universal laws, but local conditions, rules that apply only within our own cosmic bubble. Constants we consider fundamental might be circumstantial. Even the structure of time and space could vary across different regions. In this view, what we've long assumed to be foundational truths become local phenomena, like weather patterns in a single country, rather than unchanging laws of nature. Our universe becomes a province in a larger, unknowable expanse. The multiverse also redefines the scale of cosmic reality. Space, as we perceive it, is immense, yet still finite. We measure distances in light years and marvel at the void between galaxies. But in multiverse models, our entire observable universe may be a mere pocket, a sliver within a vastly larger structure. The implications are staggering. If even a small fraction of the proposed bubble universes contain matter, structure, and time, then the number of possible realities, each distinct, perhaps unrecognizably so, exceeds imagination. Some might follow familiar physical laws. Others may operate under entirely alien principles. There may be universes with no atoms, no light, no time as we know it. This diversity, while conceptually vast, may also hold answers to some of the most puzzling questions in physics. The small but non-zero cosmological constant, the asymmetry between matter and antimatter, the unexplained values of particle masses, these might not require singular explanations if there are multitudes of universes where such values differ. In this way, the multiverse is not just a canvas for theoretical excess, it becomes a framework for resolution, a way to contextualize the peculiarities of our own cosmos within a much broader statistical ensemble. It also offers a new narrative for the origin of our universe. The traditional Big Bang model describes a singular event, the birth of space and time from a point of infinite density. But in multiverse models, that birth may be one among countless others. Our Big Bang becomes local, not universal. It is a spark, not the spark, and just as stars form and die within galaxies, so too might universes arise and fade within the greater structure of reality. Creation itself becomes decentralized, ongoing, and without boundary. As this narrative unfolds, it blurs the line between the known and the unknowable. Some universes may be forever beyond observation, their existence inferred only through theory. Others might leave subtle fingerprints, distortions in the cosmic background, statistical anomalies, patterns in the fundamental constants. But even if definitive evidence remains elusive, the logic underpinning the multiverse continues to grow more sophisticated, more integrated across disciplines. What emerges from this convergence is not a final answer, but a deeper kind of question. What kind of reality do we inhabit? Is the universe a singular construct, or a shadow of something vastly larger? Is our cosmos the rule, or the exception? These questions challenge the very framework of science, urging us to expand our methods, rethink our assumptions, and accept that the ultimate nature of existence may remain forever just beyond the veil. And yet, that doesn't diminish the value of the search. If anything, it magnifies it. To peer into the dark and imagine infinite worlds, not for fantasy, but for understanding, is one of the boldest intellectual acts humanity can undertake. Whether or not the multiverse exists, the very act of grappling with the idea reshapes how we see the universe and ourselves within it. In the end, the multiverse remains one of the most daring and transformative ideas in the history of science. It stretches the imagination to its limit, offering a reality that is not singular, but endlessly branching, bubbling, and unfolding. Whether it exists as a physical structure, a mathematical consequence, or a metaphysical metaphor, it demands that we think bigger, much bigger than ever before. It challenges our sense of isolation. It humbles our assumptions about centrality. And it invites us to see ourselves not as lonely observers adrift in a vast universe, but as participants in a reality that may be unimaginably larger and stranger than anything we can fully comprehend. Yet even in the face of such immensity, our own universe remains a marvel. The fact that we can ask these questions, model these possibilities, and peer into the early light of creation, this too is a kind of miracle. Whether we are one universe or one among countless others, the journey of discovery is real. The wonder is real, and the meaning we draw from it, however local, however personal, endures. Perhaps the multiverse is unreachable, perhaps it is an illusion of mathematics or an echo of something deeper still. But if it is real, then somewhere, beyond stars, beyond time, there may be another version of you, wondering the same things, asking the same questions, reaching, as we do, into the dark. Thanks for listening. This has been Mysteries of the Universe. If you enjoyed today's episode, be sure to follow us wherever you get your podcasts. And if you'd like to support the show and unlock bonus content, subscribe to the Forbidden Knowledge Network on Patreon. Subscribe now.